Hi everyone, today we're going to go through IBSL physics topic C.1, which is simple harmonic motion or SHM. And honestly, this topic sounds much scarier than it actually is because once you understand the logic behind the motion of the graphs, everything starts connecting together. So first of all, what is SHM? So simple harmonic motion is basically a repeated back and forth motion around something called the equilibrium position. The equilibrium position is just the center point where the net force is 0. So I draw a small diagram here. So this is a pendulum, and the point in the middle is the equilibrium point, as you can see. So yes, this is the center point, and the net force here is 0. A really common example is a spring with a mass attached to it. So if I pull the mass to the right and let go, the spring pulls it back toward the center. But because the mass has inertia, it doesn't just stop at the center. It keeps moving to the other side, then gets pulled back again, and this motion keeps repeating. And this is where the important idea comes in, the restoring force. A restoring force is always directed back toward the equilibrium. So basically, the force always tries to bring the object back to the center. And that means if displacement is positive, force is negative. And if displacement is negative, force is positive. So we can say that force and displacement are always in opposite directions, as I said here. So that's why we write this formula. And this is the mathematical expression of the restoring forces formula. So the negative sign is really important here because it's there because force acts opposite to the displacement. And K is called the spring constant. Basically, it tells us how stiff the spring is. A bigger K means the spring pulls back harder. Now, before going further, also I'm going to draw you a spring so that you can imagine it more easily. This is the equilibrium point. Okay. So now before going further, let's quickly define frequency and period because these always show up in SHM questions. So first, frequency is the number of oscillations per second, and period is the time taken for one full oscillation. And they're reciprocals of each other. I wrote the formulas here. So if one oscillation takes 2 seconds, then the frequency would be 0.5 hertz. Also, this is the unit of frequency. Okay, so now something really important in SHM is acceleration. Using Newton's second law, we can rewrite the SHM equation as here. And this equation is actually super useful conceptually because it tells us that acceleration is proportional to displacement but opposite in direction, as you can see from the negative sign here. So the farther the object is from the equilibrium, the greater the acceleration becomes. At the equilibrium position, displacement is 0, so acceleration is also 0. But at the maximum displacement, acceleration becomes maximum because the restoring force is strongest there. Now let's move on to the graphs because this is the part that confuses many people. But the graphs actually become really easy if you imagine the motion physically. So first, I'm going to show you the displacement time graph. I hope you don't get confused from these dots. Okay, so this graph looks like a sine wave or a cosine wave because the motion repeats smoothly over time, and that the object starts at one side, moves toward the equilibrium here. Wait, sorry. It does. No, here it starts from the equilibrium, and moves toward the side and then moves back to the equilibrium and then goes to the other side and then it completes one period. So a period is basically the duration of a cycle, as you can see here, and this is the amplitude as I draw here. This is the amplitude, and this shows the maximum displacement of the mass from the equilibrium point. So amplitude is, as I said, simply the furthest distance from equilibrium. And now let's think about the velocity time graph. So this graph is shifted compared to the displacement because velocity depends on how fast the object is moving. At maximum displacement, velocity is 0. So that you can see more easily, I drew little dots here, but I think it makes it more complicated, so I'm gonna show you again. So here, as you can see, this is the maximum displacement. This is the maximum displacement of a mass. Imagine a pendulum as like here. So this is A is the maximum displacement. This is the equilibrium point. The ball goes to A and then it comes back to the equilibrium. And here the velocity is equal to 0 while the displacement is at its maximum. So we can say that when the axis, when A is at its maximum here, it's at 0 in the velocity graph. And oppositely, when the pendulum is at its equilibrium point, its velocity is at its maximum while the displacement is 0, because we take the base as the equilibrium point. So here, this is the base point. As you can see here, I marked it as B. Here the velocity is at its maximum, but the displacement is 0. So the last of them is the acceleration graph. So basically the acceleration time graph is an upside down version of the displacement graph, because acceleration always points toward equilibrium and it's in opposite directions with the displacement graph. So when displacement is positive, acceleration is negative, and when displacement is negative, acceleration is positive. So that's why the two graphs are opposite. And now let's talk about energy changes in SHM, because this is another huge IB concept. As the object oscillates, energy continuously changes between kinetic and potential energy. At maximum displacement here, the object stops for a moment, so kinetic energy becomes 0 and potential energy is maximum. At equilibrium, the object moves fastest, so kinetic energy here is maximum and potential energy is 0. Minimum, not always 0, but so energy is constantly transforming back and forth during the motion. And for springs, elastic potential energy is given by this formula. I forgot to write it in the notes. So this is the formula of the elastic potential energy. And notice how displacement is squared, meaning that potential energy is always positive. So if we look at the energy displacement graph, potential energy becomes forms a U shape because it depends on x squared, so it's always positive. However, kinetic energy does the exact opposite, so it is maximum at equilibrium and minimum at maximum displacement. But the total energy stays constant throughout the entire motion. As you can see here, this is the total energy. So finally, a quick note about phase. If two oscillations move together and reach the same positions at the same time, we say they're in phase. If one is opposite to the other, then they're out of phase, usually by 180 degrees, which we show by 1 pi in radius. And the last concept is isochronous oscillation. So isochronic oscillations. So this basically means that period does not depend on amplitude. So even if the oscillation becomes bigger or smaller, the time for one oscillation stays the same. And that's basically the core logic behind SHM. So basically, if you understand why the restoring force points toward equilibrium, why acceleration is opposite to displacement, and how the graphs physically connect to the motion, the SHM becomes way more memorable and much less about formulas. So I hope this helped, and good luck with your IB physics revision. Bye.